Here's a slightly more complicated circuit. This one we're going to use phasors, phasor notation. We're going to replace X with a 30 ohm resistor, then we're going to reanalyze with a 0.5 Henry inductor, then we're going to replace X finally with a 50 microfarad capacitor. Each time we're going to solve for Vx, voltage across that component, and the frequency is 50 Hertz. Going to use Supermesh each time for the analysis. After that, I'm going to Thevenize the circuit as seen by this. We'll presume this is a load, and we'll analyze for the same three components: resistor, inductor, capacitor. So if you know how to write your equations with DC analysis, you shouldn't have any issues doing this phasor notation. There's only one component here that's going to be inductive or capacitive, and that'll be X. Once again, I have shown the current arrows, whole flow, the super mesh, and a standard mesh. I have summed the currents at this node. Branch current ISM, which is the super mesh, enters 0.05 Vx. The voltage controlled current source enters. So both currents enter. The only possibility is they both exit. Supermesh plus 0.05 Vx for the current in this perimeter of the supermesh. The most difficult part of any physics equation writing is writing the initial equations. Once we have something to work with, well, it's pretty much routine after that. Here we replace X with a 30 ohm resistor, and I'm using again supermesh analysis, and these are the two equations, ISM and I1, two equations with two unknowns. The two unknowns, ISM is unknown and I1 is unknown, and we want to solve for I1 so we can find our Vx voltage. And there are many ways to write the equations and to represent them in a particular form. I'm not going to discuss any of that. That's a whole another situation. You're going to have to read the books. You can find a lot of information in the books. Don't try to memorize anything. If you hear something and then you memorize it, well, that's all you're going to know. You got to really have a conceptual understanding of what to do. And yes, there's a lot of implicit things going on here. Implicit meaning they're not shown. This is all we need to see. Actually, again, the arrows we don't even really need to see. It just points out that the ISM supermesh is defined in this branch and the I1 is defined in this branch. It's possible, and like I say, in a bigger circuit, as I've said in another tutorial, in inner loop, it's possible there's a mesh over here, and a mesh over here, and a mesh here, and a mesh up here, where all four branches are shared. And so we can still draw a mesh inside of here. It's still a valid mesh arrow, but this mesh is not defined by any particular branch because there's another mesh current going through it at the perimeter. So we could never actually measure a mesh current in this situation, but we could calculate it. Here I can actually measure the current in the 10 ohm resistor to find what the supermesh value is. Here I could find the I1 current value by measuring the current in the 30 ohm resistor, or I could measure the current perhaps in the X load. The writing of the initial equations, like I said, is the most critical part of everything. Here I've repeated supermesh equation and the I1 equation for both meshes. Here I have supplemental equations. Vx, which is at our load, is equal to 30I because we replaced X with the 30 ohm resistor. And then the voltage controlled current source, 0.05 times Vx, which is 0.05 times 30I, 1.5I is equal to that. A little bit of basic algebra we reduce to get Vs, a little basic algebra of the I1 mesh, and we end up with the equation here. We can add this equation with this equation, and we multiply this by 1.5 to make the supermesh values equal -90, and then we already have 90, so they'll cancel out. And this is all we have. We have Vs equals 105 times I1. Coming up here, we can easily find I1 because we have Vx divided by 30. Wow. Actually, we have Vs, excuse me. We have Vs divided by 105 is equal to I1. And then we can find Vx is equal to 30 times I. And again, substitution, 207, or 200 divided by 7. And the phase shift is 0. And it's interesting to note our load in the X component is a resistor, and the phase shift between the current and through the resistor and the voltage across that resistor are the same. They both happen to be 0-degree phase shift, but they are the same because there's no phase shift going through a resistive element. It's not necessarily that there's both 0, but they are both the same. Here we replace X with the 0.5 Henry inductor, and we still solve for Vx. And we're still using same supermesh. And as I commented over here, these two equations of the supermesh and I1 are almost identical to that when X was replaced with the 30 ohm resistor. With a 30 ohm resistor, we had 30 plus 30 plus 60. Here we have the impedance of the inductor, which is 50 pi at 90 plus 90 degrees phase shift. But the ISM supermesh equation does not actually, you'd make use of the X load. So this one actually looks exactly the same. So a lot of our work has already been done when we used our 30 ohm resistor. Continuing where X is equal to the 0.5 Henry inductor, we have supplemental equations. Vx to the inductor impedance times I1 and the 0.05 Vx. They look a little different this time. Here's the supermesh equation repeated, and after we simplify it, that's the result. The I1 mesh equation repeated, a little bit of basic algebra, and here's the result. And we're going to add Vs with 0. Again, we're going to multiply by 1.5, so our supermesh value will cancel out. Some simple addition, and we have Vs is equal to, in a rectangular format. Coming up here, we rearrange again with Vs. We find I1 is equal to this. Here we replace Vs with the source voltage, 100 volts, 0 degrees. That was given to us. Vx is found this equation here, substituting in the inductor. We already have I1, substituting in for I1, and we come down here, Vx, well, there's a little bit of number crunching there again, but still basic stuff everyone should be able to do. And a final multiply in polar form, and we have Vx. Here's the voltage across the inductor. Now we replace X with a 50 microfarad capacitor. Again, the supermesh equation, nothing new going on. I1, again, this particular part here is now capacitive impedance. Again, both equations very similar when we use the resistor. I repeated the Supermesh equation and repeated the I1 mesh equation. A little bit of basic number crunching with VS. Again, more number crunching. We already have our source equations to work with. So this is straightforward, should be. And Vx looks a little different. Capacitor impedance, 10.05 Vx, supplemental equations. So repeating the equations, we're going to add, once again, we're going to multiply by 1.5 again, so our Supermesh cancels out, and we're left with Vs equal to a similar looking result. Basic algebraic manipulation to get I1. Here we have Vx. We're going to substitute I1. So Vx is a little more, well, it's a little messier to look at. Then we have Vx multiplied by this mess here. Yeah, here's the voltage across the capacitor, 64.71 volts, with a negative 49.67 phase shift. It's interesting to note the result here. Well, I never solved for Supermesh value. We weren't asked to solve for the Supermesh current value, and we never did. We always multiplied by 1.5, and that conveniently canceled it out because we always needed to find I1 so we could find the load voltage Vx. And it's interesting when we do the inductor and cap, there's always a 75 ohms there. Those were 3 Supermesh analysis. Next, we're going to do the same circuit. We're going to Thevenize it, as seen by the X terminals. Thevenize, as seen by X. X is assumed to be the load. ISC is short circuit current. VOC is the open circuit voltage. I'm going to find the short circuit current first. Short circuit current flows through the 30 ohm resistor branch. Because this is now shorted, Vx 0 volts, thus 0.05 Vx. This current source is 0 because it's a current source and it's off, 0 amps. It's open, so all we have is these 2 loops. So the short circuit current is going to be source voltage divided by 10 plus 20, and then we have 30 and 60 in parallel, and then we have a current divider times 60 over 60 plus 30, so we can find the current in this branch, which is the short circuit current, equals 1.333 amps, 4 over 3 amps. Now we're going to find the open circuit voltage. 30 ohm resistor has 0 amps. There's no voltage across this because this is open. There's no current flowing through the 30 ohm resistor. That also puts VOC across the 60 ohm resistor because there's no voltage drop across the 30. No current, no voltage drop. Thus Vx is equal to VOC. Vx is equal to VOC. So we have a single loop here. Vs equal to 10 times that. This is pretty much basic for a single loop here. That's exactly what that is, a single loop right here. That's what we did here. A little bit of substitution. After we find ISM plus 0.5, Vx is equal to VOC over 60. We find that ISM is equal to minus 1 over 30 VOC. So ISM substitution, negative 1 over 30 VOC for ISM. And we get these results. We end up with replacing our voltage source with the value, the phasor value. VOC is, surprise, equal to 100. 0 degree. It's VOC is equal to Vs and the Thevenin equivalent. I repeated the values here, ISC and VOC, for reference. We can calculate the Thevenin resistance, VOC divided by the short circuit current, and because of the polarity and the short circuit current arrow directions, we have a positive Ohm's law, and we find that number I pointed out before. Interesting. 75 ohms is the Thevenin resistance. Now we have the Thevenin equivalent as seen by X load, and we can replace X with any value we want, R and L, C, and I've repeated the number crunching here, and after Thevenizing it, which wasn't that difficult, we can find Vx for the 30 ohm resistor, the 0.5 Henry inductor, and the 50 microfarad capacitor. Much easier and faster. This circuit came from the book Engineering Circuit Analysis, and they actually said to use the PSpice to analyze using the SPICE circuit simulation program, but hand analysis, not that difficult. Coming up is a bonus circuit. Here's a bonus circuit to analyze. We have a voltage controlled voltage source, VCVS, one single series loop. VA is defined here. It has to be fully defined because it tells us how to connect voltage VA, 2 times VA, how this is going to respond. So we need to fully define the vector quantity of the VA voltage. I also added a polarity across a 30 ohm resistor. I only did that because I'm going to sum the V rise equal V drops on this path to help verify. Even though I only really needed, we're only asking to find I, and I found I here is 8 amps. You can do that and then stop, but it doesn't hurt to do something extra to check the validity of this answer. We could find all the powers in this circuit too, to even if we needed to know that, but something else to help verify, check our results. So we have our single loop, and here is our single loop equation here, a supplemental equation to find VA, substitution using our original equation and substituting in the supplemental in here. After we have our initial equation, that's the hard part. Again, there's a lot of implicit stuff going on here that isn't being talked about. So we have basic crunch here. I is 8 amps. And now we can find VA. There's a negative 120 volts. And 2VA is minus 240 volts. And when we set up our V rise equal V drop, or you could even run a KVL, same thing. V rise 120, VA is a V rise. The drop's V30, positive negative, that's a drop. 2VA, voltage controlled voltage source, plus to minus, going clockwise, of course. That's another drop. And of course, so we're all using whole flow, passive sign convention. I is a whole flow current. All the currents in the previous circuits, all whole flow, all using passive sign convention.